In this lesson, we'll look at the magnetic field of a current-carrying wire and then at the magnetic field of a solenoid, or a coil of wire. And here are your objectives. In the previous lesson, we saw that a wire that's carrying a current, when placed in an external magnetic field, will experience a magnetic force. Now we're going to see that a current-carrying wire generates its own magnetic field around it. So this is a simulation. You can see the URL here at the top, and right now we've got two cells connected into a battery in series in a circuit, and we've got a compass that's sitting behind or below the wire. Right now there's no current flowing through the circuit because the switch is open, and therefore the north pole of the compass points northward, as is shown here. When I close the switch, however, we see a deviation so that the north pole of the compass points downwards. Remember that the direction of a magnetic field is defined as the direction that the north pole of a compass points. And so what we're seeing is that by closing the switch and allowing a current to flow through the wire, we get a magnetic field that, at least behind the wire, is pointing downwards. If I move the compass now so that it's on top of the wire, we'll see that the north pole instead points upwards. Now I'm going to move it on top of the wire, so it's in front of the wire, closer to us than the wire is, and we see the north pole points upwards. So the magnetic field above the wire is pointing upwards, but below the wire it's pointing downwards. And in fact, if I switch the direction of the batteries, watch, I'll flip the batteries in a moment, we'll see that everything reverses. So I flip the batteries, and now the magnetic field is pointing upwards below the wire, and it's pointing downwards closer to us than the wire. And if I open the switch, then the magnetic field disappears, and the north pole of the compass again points towards the north pole of the Earth. This is known as Ørsted's experiment, or Ørsted's discovery, because Hans Christian Ørsted, a Danish physicist in the 1800s, was the first to observe this. So what we can see is that we've got a direct current through the wire, and it's generating a magnetic field around the wire, as evidenced by the deflection of the compass. Now by moving that compass all around, we could map out the magnetic field. Here's a wire. Let's say we had a conventional current moving to the right. Remember, we're always talking about conventional current, or the movement of positive charges. If we move that compass around, we would see that the compass, when it is closer to us in front of the wire here, let's say it's right there in front of the wire, is going to have a deflection of the north pole downwards. That means the magnetic field here in front of the wire is pointing downwards. And if we were to put it back behind the wire over there, let's say, then we would see the opposite, that the north pole of the compass points upwards. And by doing that all around and allowing the compass to rotate in 3 dimensions, we would actually see that we could map out magnetic field lines forming concentric rings around the wire. So something like this, where in front of the wire over here, the magnetic field is pointing downwards, the north pole of a compass would point downwards, whereas back here it's pointing upwards. Now it's hard to draw this in 2 dimensions, but this side over here is meant to be closer to us, and this side over here is farther away from us. To illustrate that in a different way, imagine taking this end of the wire and tipping it towards us so that the current was pointing out of the page like that. So this is the wire with the current coming out of the page towards us, and then what we would see was that the magnetic field lines are in concentric circles around it. They get farther apart from each other as we go out from the wire because the magnetic field is weakening, and this part that is closer towards us therefore points like that. So the magnetic field lines point in that direction. Again, I've taken this end and tipped it towards us so that we're looking at it end on. Now experimentally we can find that the magnetic field strength is proportional to the current. If you double the current, you will double the magnetic field strength. Also, the magnetic field strength around the wire is proportional to 1 over the distance from the wire, r being the distance from the wire. And that's shown here by the fact that the circles are getting farther and farther apart from each other. Remember that the density, or the closeness, of magnetic field lines indicates the strength of the field. So as we go farther out, as r gets bigger, the field gets weaker. Now, in terms of remembering the direction that the magnetic field lines point, we use a new right-hand rule. And that right-hand rule is that we now point our thumb in the direction that the current, the conventional current, is traveling along the wire, and then the fingers of our right hand will coil in the direction of the magnetic field. So here's your right hand, you point your thumb in the direction of the current, and then your fingers will coil in the direction of the magnetic field. Notice that your fingers in front of the wire are going to be coiling downwards, and if you were to tip your hand backwards, you'd see that behind them they're pointing upwards. And that also allows you to work out the field direction on top and below the wire. You just rotate your hand back and forth, keeping your thumb pointing this way, and the curl of your fingers will indicate the curl of the direction of the magnetic field lines. So we've seen that a wire placed in an external magnetic field will experience a force, and we've also seen that a current carrying wire generates its own field. What if you have two current carrying wires placed next to each other? Well, let's say that we've got two current carrying wires, both with conventional current moving towards the right. Let's take a look at the one on the top. The one on the top will generate a magnetic field around it, and using the right-hand rule that we've just worked out, we can see that above the wire, the direction of our fingers on our right hand, if we point our thumb to the right, is out of the page, and therefore the magnetic field will be out of the page. And it's going to get weaker as we go farther away. And I'm trying to indicate that by increasing the spacing. Below the wire, again using the right-hand rule, we see that our fingers curl back into the page, and so the magnetic field from this top wire is back into the page. Now, this bottom wire is sitting in that field, and the field extends even beyond the wire as well. So what I'm drawing here with these X's is the magnetic field generated by this top wire. Now, the bottom wire, though, is a current-carrying wire sitting in an external magnetic field, and thinking back on the previous lesson, we know that it's going to experience a magnetic force. So we point our fingers in the direction of the current, that's towards the right, we fold them in the direction of the magnetic field, that's into the page, and our thumb, therefore, is left pointing upwards. And so the force on the bottom wire, the magnetic force, on this bottom wire sitting in the magnetic field generated by the top wire is upwards. Now we could repeat that whole process, drawing in the magnetic field for the bottom wire and looking at the force on the top wire as a result of it, and we would see that the force on it is pointing downwards. Or we could just reason that by Newton's third law, the force of one wire on the other must be equal and opposite to each other because they are a Newton's third law pair. So what we see here is that two current carrying wires with current moving in the same direction experience a force that pulls the two of them together, an attractive force. And these two arrows, although I haven't drawn them equal in length, should be equal in length because this is a Newton's third law pair. What if the currents are going in opposite directions? Well, again, let's look at the top wire. The top wire now is going to have the same magnetic field as we saw before because we haven't changed anything with the top wire. And so down here we see the same field pointing into the page. But now the next right-hand rule that we have to use, the right-hand rule for a current carrying wire sitting in an external magnetic field, tells us to point our fingers of our right hand towards the left, fold them in the direction of the magnetic field into the page, and we see now a force pointing downwards. And either by repeating that process or by reasoning from Newton's third law, we would see that the force on the top wire is upwards. And so we see a repulsive force between two current carrying wires where the currents are pointing in opposite directions. And actually, this is how the ampere is defined. The ampere is a defined or a fundamental unit, and it's defined as the amount of current that needs to flow through two very long parallel conductors if you place them 1 meter apart to generate a particular magnitude force, a force of 2 times 10 to the negative 7 newtons. You don't need to remember those numbers, but it's helpful to remember that the ampere is a fundamental unit and that the coulomb is actually then derived from that as the amount of charge that flows when 1 ampere flows through a conductor for 1 second. It's easy to think that the coulomb is the fundamental unit and the ampere is derived, but it's actually the reverse. Now, what if we take that current carrying wire and bend it into a loop? So here we've got a loop, and let's say we have a current flowing in this direction. Using that same rule, pointing our thumb downwards here and coiling our fingers, or pointing our thumb upwards here and coiling our fingers, we see the same thing. We see that the field inside the loop is going to be into the page, and outside the loop it's going to be out of the page. And I'm not drawing with any particular concern here to showing the field strength. The field strength will get weaker as we go farther away, just to show the direction. And if I reverse the direction, so instead of going clockwise here, I go counterclockwise, then I see the opposite. The field inside the loop is pointing out of the page, and outside of the loop it's pointing into the page. Again, I'm not really being careful to show the field strength diminishing as you go farther away. Now, if you were to take a bunch of those loops and line them up together, you'd get a coil, or what we would call a solenoid. And here I've got a cylinder that I'm going to wrap that coil around. So here you can see I've run a wire up and I'm wrapping it around this cylinder to make a coil of wire, and the current is shown here by the arrows. Now you can see that this is effectively a bunch of these coils, if I tip this edge towards me slightly, stacked up together. And so the magnetic field generated by each of those is going to reinforce those of the others, and so the net magnetic field is going to point into the coil, into what we call the solenoid. So I'm drawing the X's not to mean it's going into the page, but that the magnetic field is pointing into the coil here, and it's going to point out of the coil on this end as well. That might remind you of a magnetic field we've seen before with a bar magnet that has this as the north pole and this as the south pole. The magnetic field lines emerge from the north pole of a bar magnet and go back to the south pole like this. And it turns out that the magnetic field of a solenoid is indeed similar to that of a bar magnet. So here we see that if the current is looping around in this direction, then the north pole of the solenoid, which acts like a bar magnet, is over here. And we can remember which pole is the north pole with one more right-hand rule that I've tried to draw in here. We take our right hand, we grip the solenoid so that our fingers are curling in the direction of the conventional current, just like I've shown here. That leaves our right thumb pointing in the direction of the north pole of the solenoid. That means that if we reverse the direction of the current, like I've shown here with the current going this way, again we grip it with our right hand and our thumb points over here, so this is the north pole and this is the south pole. So we've reversed the polarity of our solenoid. So that's a look at the magnetic fields that current carrying wires and solenoids generate around them.